let me recap a little bit where we were last time. So I tried to explain that the main idea was initially was to try to find some differential equation that the potential would satisfy, but then we decided that maybe that was not quite the right idea because the solutions to the differential equations there were not well determined by the initial conditions. But there was some other space which mapped to our space where we were looking for the solutions. And there, the solution to the differential equation was well defined. So I need to explain again the source of this differential equation really quickly. So let me remind you where we were last time. So if VB is a DG vector space, in other words, a complex of vector spaces, and it has a circle action, which is some operator B from V to V shifted by -1, so a degree +1 homological operator, satisfying B squared equals to 0 and BB plus BB equals to 0. So this is what would come from the singular chain complex of a space if the space carried a circle action. That would be the standard example of that. And a pairing with respect to which B is self-adjoint. So this is one of the things that you now need. What we were doing is we were thinking of this as a symplectic vector space with respect to a certain residue pairing constructed from this ordinary pairing. And we were taking the Fock space, and the Fock space had some natural differential, which was not the natural differential on the symmetric algebra. In any case, the moral of this, we were getting an operator delta, which I'll remind you what it was. So it went from sim V to sim V, sim V minus to sim V minus. V minus, as before, means V adjoined U inverse for this variable U of homological degree -2. And what this delta does on symmetric 2 tensors, so just a tensor product of 2 elementary tensors, so something like x u to the I tensor y u to the j, it was giving 0 if either I is not 0 or j is not 0. And the special answer it gave was x paired with b of y if I equals to j equals to 0. So notice that what this does is it decreases the symmetric tensor degree by 2. You took a symmetric 2 tensor, a product of 2 things, and it gave you a scalar. So it looks a little bit like a differential order 2 operator, like something that takes 2 derivatives if you wish. So then delta was extend this to a full second order differential operator on all of sim V minus. And I wrote last time a formula. What you do is you basically sum up in all possible ways a way to choose 2 terms in the symmetric tensor and apply this operator delta. And then the origin again was the fact that this Fock space associated to this vector space V was isomorphic to sim V minus and then a joined formal variable h bar with differential b plus ub, which would be the natural differential on sim V minus, but then, sorry, not just b plus ub, you also add one more term, this h bar delta. So I told you that when you do the construction of the Fock space, you get a natural differential on it. As a vector space, not as a DG vector space, the Fock space is isomorphic to sim v minus double bracket h bar. And then when you pull back the differential, you see that it's not the same as the natural differential you'd have on the right-hand side. You have an extra term, and that was the origin of this operator delta. And this is an easy exercise if you try to write down exactly where this delta comes from, and very useful to figure out where to check your understanding. So now, I claim that what we have constructed from this data, we have constructed a BV algebra. A Batalin-Vilkovsky algebra. So I'll remind you what that means. It's a commutative DG algebra, which consists of an algebra, a multiplication, and a differential. And it has a second order differential operator, delta, of degree -1, +1 homologically, sorry, such that delta squared equals to d squared equals to d plus delta squared equals to 0. Okay, this is what a BV algebra means. This is a definition. Probably Ezra Getzler should be given credit for giving to mathematicians this meaning. Now, one of the consequences of having a BV algebra, we automatically get from it a Lie bracket. Which I will call like this. And this is defined, I'm going to ignore signs for time being, but then it makes sense in the DG setting. So it's measuring the failure of delta to be a first order operator. If delta was a derivation, the right-hand side would be 0. This is measuring this. And the fact that delta is second order says that this is a first order operator in each one of the variables, x and y. That's one of the Grothendieck definitions of being second order. And the fact that it's a Lie bracket is not particularly hard. Of course, there are some signs here. I don't know, maybe here it's -1 to the power degree of x and something else, I don't know. It's an exercise to check that it's a Lie bracket. And moreover, so this gives the space A structure of a differential graded Lie algebra with bracket, where this is my bracket, but the differential on that bracket is d plus delta, not d. Whenever you see a DGLA, the very first thing that should cross your mind is, now you want to solve the Maurer-Cartan equation. Probably the only differential equation that I know, being an algebraist. And this, it's the following differential equation, d plus delta x plus 1/2 x bracket x equals to 0. So this is often called, when we're looking at a DGLA of this particular sort that came from a BV algebra. There are, of course, many DGLAs that don't come from a BV algebra, but when they do come from a BV algebra, this is sometimes called the quantum master equation. And I'll abbreviate it as Q. All right. Fantastic. This will be the differential equation that I have been talking about all along. This is the equation that we care about. So let me repeat a little bit. What we have done is we started with a vector space, a DG vector space V with this two pieces of data. That's what you should keep in mind. You start with the differential graded vector space with a circle action and a pairing. From it, we constructed a BV algebra. And in this BV algebra, it's natural to write down the quantum master equation. That is our plan of attack. So in our particular case, we will be most interested in this in the following setting. We take L, I remind you, was the Hochschild chains of the algebra A, shifted in degree by D. So A is Calabi-Yau A infinity algebra of Calabi-Yau dimension D. Maybe let me call this cyclic A infinity algebra, the same thing, of Calabi-Yau dimension D. I take L to be the DG vector space consisting of Hochschild chains of the algebra A together with the Hochschild differential B. It has a circle action given by the operator big B, the con operator. If you don't know what that is, it's something of the following sort. I'm going to write it again without signs, but something like B of x bar y, for example, will be 1 bar x bar y plus or minus 1 bar y bar x. So what you do is you take your tensor and cyclically permute its inputs and put a 1 in front. So it obviously increases a Hochschild degree by going from a 2 tensor to a 3 tensor. And then there's another operation on the Hochschild chain complex called the Mukai pairing. Which I introduced maybe 15 years ago for homology, but it makes sense at chain level, as was discovered by several people. Maybe Shkliarov was the first one to discover this, and then there are many origins for this. Maybe it's definitely in Kontsevich-Stoibelman. So this is a pairing on L, which in our case will have some degree, maybe minus 2D or 2D. I don't remember if it's positive or what its degree is, but it's something of that sort. I'm going to ignore even shifts anyway. So this Hochschild chain complex of my cyclic A infinity algebra carries these two structures, so I can do all the construction that I've told you before abstractly. I can do it for my algebra. So the conclusion is sim L minus, where again L minus means I joined this formal variable U inverse, and I'm gonna put two variables, H bar lambda, is a BV algebra with respect to the operator delta that I defined a page or two ago. And we will be interested in solutions of the quantum master equation. And the solutions of this quantum master equation will look like the following thing. F, maybe A, equals to summation F A G N, H bar to the G, lambda to the 2G minus 2 plus N. These will be the solutions, and I will fix one initial condition where I want F. Actually, I'm not going to tell you yet what the initial condition. I'm just going to tell you which thing I'm fixing with fixed F03. F03 should be something like the product in the ordinary product in the well, actually, yeah, let me not say what F03 is yet. All right. Before we go any further, I want to tell you, you might be a little puzzled. Okay, well, we know somehow by some hearsay that if you have a DGLA, we are interested in solutions of the master equation or of the Marder-Cartan equation. But in the case of this particular type of DGLA that we obtained from a BV algebra, obtained exactly the way we did it from a pairing and a circle action, there is a very important theorem which says the following thing. An element x in lambda times sim v minus double bracket h bar and lambda is a solution of the quantum master equation if and only if b plus ub plus h bar delta e to the power x over h bar equals to 0. Moreover, x and y are gauge equivalent if and only if the homology class of x equals to the homology class of y. Actually, I don't know. Let me write it in words because this notation is maybe not completely obvious. X and y are homologous. And then this equation holds in some kind of completion again in sim hat h bar v minus h bar lambda. So ignoring the technical details about where I'm defining this e to the x over h bar, and why on earth do I need this extra variable lambda, which I do need in order to make sense of some finiteness conditions. The main point is that if you construct yourself a BV algebra by starting with a vector space V with circle action and pairing, the way I said in the beginning, then the homology of the Fock space, of the abstract Fock space constructed from V, is isomorphic to the space of solutions of the quantum master equation up to gauge. And when I say up to gauge, this is in the sense of deformation theory. For those of you who have not seen this before, the solution, there is a natural action of a formal Lie group of on the space of solutions of the quantum master equation, and we are only taking equivalence classes. But this is not very important. The main point is that we have a way to go back and forth between solutions of the quantum master equation and homology classes in this particular vector space. This is, by the way, it's an important theorem, but I can definitely leave it as an exercise. This is not a hard calculation to check. You just do the calculations order by order in lambda, and then in h bar. Any questions? Let me stop so far here before we go any further. This has been a lot of kind of algebraic preparations for what we are doing. So to summarize, exactly what I've been saying is, if you start with a vector space with these three, a DG vector space with these two extra structures, somehow miraculously we construct this so abstractly we construct this Fock space from it, but which has a very concrete incarnation as a particular symmetric algebra with a new differential operator, with a new differential, sorry, not differential operator, square zero differential. This will be a differential here. And to understand the homology of the Fock space, we need to understand solutions of the Maurer-Cartan equation, which are in one-to-one correspondence with homology classes by this relation. Any questions about this? All right, if there are no questions, now I want to explain to you the geometric origin of this quantum master equation. And this is the work of Zwiebach and Sen, two physicists. The idea is the following. When we think about the vector space with the circle action and the pairing, really we should think about this circle action and the pairing as coming from some kind of action on some moduli space of some very simple Riemann surfaces. So if I'm looking at moduli spaces of Riemann surfaces, but which just consist of disjoint unions of annuli. So that's a very simple thing. If I take singular chains on that, I get something that has some very simple generators. And the generators are the following thing. I could have the tube, so of, if you want, framed annuli, all my Riemann surfaces will be framed. So the generators turn out to be something like this. Think about the tube, but it's framed. So I have a point on each boundary circle. And this corresponds to the identity. If I think about C0 of this as an element in C0, so maybe let me write it. Now, another interesting element that I have is what I like to depict like this. It's a one chain in the moduli space of annuli. So it's a cylinder with two framed ends, but because the one chain, it's a whole one-dimensional family of these. And so the one-dimensional family keeps one of the framings fixed and rotates the framing on the other one. Does this make some sense? It's an operation with one input and one output in my field theory, if you want. But it's of degree 1. It has, as a movie picture, if you want, you see one end staying fixed and the other one is rotating by 360 degrees. And this corresponds to giving me the circle action under the TFT. So if you think about, I'm thinking about a very small set of Riemann surfaces in the moduli space of Riemann surfaces, and I'm thinking about their image under a field theory. And the ones that I'm thinking about are first the cylinder of degree 0, of homological degree 0, then the cylinder of homological degree 1, and then there's another one also in C0, but which looks like this. So it's a degree 0 cube, but with 2 inputs and 0 outputs, and this corresponds to the pairing. So you might be wondering, okay, why don't you consider this tube, but with its version in C1, where I rotate one of its framings? That corresponds to the composition of this guy with that guy at one of the ends. Similarly, you might ask, why don't you think about the tube with 2 outputs and no inputs? And I'm explaining to you that this will never be considered because we never allow things with 0 inputs. If you remember, we were having this special condition about all our Riemann surfaces having at least 1 input. So if you think about these as generators for a prop, you get what we call the prop of annuli, and this gives you the kind of the intuitive reason why L has all the operations that it has. So there's a circle action because on L, I have an action of the full prop of all chains on Riemann surfaces. So in particular, I have these 3 basic chains on Riemann surfaces, one which turns into the circle action, one which turns into the pair. Okay, all right. So what Zwiebach and Sen noted that an analogous construction, an analogous BV algebra structure to the one on L, or whatever, sim L minus, exists already on chains on MGN. Framed mod sigma n minus h bar and lambda. This is what I called the Fock space of chains on moduli spaces. So you see, this sigma n is analogous to the fact that we took symmetric algebra. This minus is still the same minus as before. I've added some u things. Oh, sorry, there's no minus here. Sorry, I should have said S1 invariance, which is the same thing as chains on MGN unframed sigma n minus. So somehow there's a very strong analogy between this guy and the former Fock space that I was constructing. I'm not going to try to go into all the details, but the point is that the fact that we're taking symmetric algebra invariance here is equivalent to saying that we are taking symmetric algebra before here. The H bar and lambda are there for the ride. The S1 invariant, sorry, there's no UB here. The S1 invariant corresponds to the fact that we're putting this minus here, we're adding this U inverse variable, and so on. And we're getting rid of the frame. So notice that, in fact, the circle action on the frame moduli spaces is free. So taking the S1 invariance is the same thing as removing the frame. All right, so the question is, so all I'm saying here in rather vague terms is that this space has a BV algebra structure. Where I can tell you what the operator delta is. What it does is it takes a Riemann surface with a bunch of inputs and a bunch of, sorry, I take this back. Here we're really talking of MG0n. We're thinking of all our Riemann surfaces as having no inputs. So I have some Riemann surface here, and what I do is I pick two outputs and sew together the pairing to them. So these have all framings, and I sew this thing, and I then sum over all the ways to do this, to choose two outputs. So you see how this is entirely similar to what we were doing. Before, we were saying, oh, and sorry, this is not sewing directly the Mukai pairing. I'm also sewing in between at one end this operator which does a circle rotation. So you should compare this with the fact that I had my x u to the I tensor y u to the j maps to x paired with by. This is exactly word for word what we have done. If somehow this, I applied the TFT functor, the field theory functor to this picture, I would think of this as having some output x u to the I here and y u to the j here, and maybe z u to the k here. And then I'm summing over all the ways of choosing two of the tensors and applying this if I equals to j equals to 0. And you're seeing exactly the pairing coming from this tube and the B operator coming from this circle action. Are there any questions about what this operator delta is at chain level? I want to emphasize that this is not a particular instance of our previous construction, because we don't start with a DG vector space with circle action and pairing. We're starting with something which is more complicated. This MG0Ns have something like a pairing and something like a circle action, but it's not really that. This chains on MG0N are not the tensor power n of a fixed DG vector space as we had before. But other than that, the picture is exactly the same. Any questions about it? I hear a deafening silence. Maybe I should really stop and wait and see. Maybe in the chat, some people will come up with questions. Or is everybody completely lost? Or
I think it's very clear.
Very clear. Good. All right. Then let me explain the main point. Is that a solution of the QME in this BV algebra, what I called f of c, has a geometric significance. And in fact, here is the theorem, which is due to Zwiebach, Sen, and Costello. It says the following thing. So a solution to the QME in f of c of the form v equals to, I'm going to use this script v, summation over g and n vgn h bar to the g lambda to the 2g minus 2 minus 2 minus n plus n, where so can be found of the form this, where the VGNs have a geometric significance. And I'm going to write it in quotes because I cannot really make sense of it very precisely like this. But all Riemann surfaces sigma in MGN says that in the hyperbolic metric, sigma has no geodesic of length less than some epsilon. So the trouble is making sense of this epsilon, but let's not worry about what this epsilon means. A very small, let's say a very small number. I will explain this geometrically in a second, but the Costello contribution is that, moreover, any two solutions satisfying the initial condition that V03 equals to 1/6 the fundamental class of M03 are homotopic, i.e. gauge equivalent. So the main point here is this is our source moduli space, our source place where we want to solve the quantum master equation. And here the solution is unique up to this, up to homotopy, that's fine. So when we're looking at in homology, that's kind of unique by the theorem that I told you about, relationship between solutions of the QME up to gauge and homology classes. So this is, we're going to solve the quantum master equation in f of c, and then map the solution to our f of L, the Fock space of L, that's what we wanted. We're going to get a very special solution of the quantum master equation there. That will be the quantum master, the solution that we want. So the idea of the proof is actually the following. It's a very beautiful idea due to Zwiebach and Sen. So let's think for a second, what is the boundary of VGN? So VGN is a subset in the moduli space of curves. It's a closed subspace because I put strict no, that means that all the geodesics have lengths greater than or equal to epsilon. So what's the boundary? The boundary will be exactly the point where sigma has a geodesic of lengths exactly epsilon. Okay, And if you work up to codimension 1, this should be unique. So now let's say I have some Riemann surface. Actually, maybe let me try to redraw it because this is not very good. So let's say I have some Riemann surface, which has, through some deformation, acquired a geodesic of length exactly epsilon. Well, what happens if I cut here? Well, there are two possibilities. Case one, either the surface that's left, surface after the cut, is connected. Then that means that this sigma, so let's call it that one sigma prime. Then that means that sigma was obtained from sigma prime by sewing two of its boundary components. Okay? So this was exactly what I was calling the operator delta. And then case two, the surface after the cut is disconnected. Let's call the two components sigma prime and sigma double prime. So that means that sigma was obtained from sigma prime and sigma double prime by doing a bracket operation. So if you think a little bit about what the bracket means for the operator delta that I just showed you here, when you look at the definition of the bracket in terms of delta, what the bracket says is you take two surfaces, maybe with a bunch of inputs, and another one, maybe. So these are complicated surfaces. And what you do is you connect one of the outputs of one with one of the outputs of the other with the circle action in between. You twist so one, the output of one with an output of the other. All right? So then when you look at what this says, this, oh, and let's notice here that something special is happening. Because I assumed that epsilon, that this geodesic was the unique one of length epsilon, then what I do see is that this sigma prime has no geodesic of length less than epsilon. And same for these. So what this, the moral of this is, what have we said? I've said that the boundary of VGN consists of two things, either things that I could have obtained by sewing together two outputs in something of genus G-1 and with n plus 2 inputs. Plus, and there's this one half factor, let's not worry about them, VG prime n prime, VG double prime n double prime, where G plus G prime equals to G, and n prime plus n double prime equals to n plus 2. So the whole moral of this is that if you take your definition of VGN to be this, the quantum master equation, which you should recognize, this is exactly the quantum master equation, is saying that you are writing one chain the boundary of a certain chain as either stuff that you've obtained by taking delta of lower genus chains, or taking bracket of chains of lower genus and more points. So maybe let me give you one example, one practical example that you can understand, that we can understand quite nicely. What is V11? Well, we are looking at the moduli space. We are inside M11. So M11, as people know, if you ignore stackiness, is isomorphic to P1, which is S2, the two sphere. Now there is one special point, sorry, this is M11 bar. There is one special point here which corresponds to the nodal elliptic curve, which topologically looks like a torus that has been pinched. Okay? Now, what do elliptic curves that are within epsilon of that point, that are close to that point? Well, those look like tori, which haven't yet quite been completely pinched, but which have a very small geodesic. They have a very small epsilon geodesic. So that's what these are. But then when I think about them, let's not forget that we had to have one marked point anyway everywhere. Frame. But how do you get these? There's several of them. There's not just one. There's a whole circle's worth of them. Those are obtained by taking a pair of pants, a framed pair of pants, and doing twist sewing on two of the boundary components. So if you take a pair of pants, put the unique hyperbolic metric there's a whole S1's worth of ways to sew two of the outputs, two of the marked circles. There's a whole circle's worth of complex structures you get. And if you made these boundary circles have radius, circumference epsilon, what you will end up with will be an elliptic curve with an epsilon geodesic. You're going to get exactly this guy here. So what this says is that this circle can be thought of delta of V03. And then the quantum master equation says that the boundary of V11 should be the delta of S03. If you expand in H bar and delta, this is the only term that can contribute to the quantum master equation. So that says that what V11 should be, it should be some kind of chain in the moduli space M11. So notice that it doesn't touch at all M11 bar, whose boundary is exactly this circle, which is delta of S03. So everything should kind of come together for you. So S03 is zero dimensional. It's the fundamental class of M03, which is a point. Delta increases chain dimension by 1. So delta of S03 should be a real one-dimensional chain. And we want S11 to be something whose boundary is this delta of S03. So we see a circle on the sphere which surrounds this special point, and we want a chain, or a closed subset if you want, in the sphere, whose only boundary is this circle, and it does not touch the boundary component of M11, the special point. So this is the only possible solution. So this, you can think of this defines recursively V11. And the fact that there was only one solution up to homotopy is a consequence of a very standard fact about moduli spaces of curves. So this VGN unique up to homotopy is just the fact that H 6G minus 6G minus 7 plus 2n of MGN is 0. So not only is top homology, this would be the dimension of the homology of MGN, one step below. So the top dimensional homology is certainly 0 because it's a non-compact manifold. The statement is that one below that is also 0, and this is a standard known fact. Any questions about this? So this should give you an idea of why solutions of the quantum master equation do show up for us, because we are fundamentally integrating over these non-closed chains. That's what the action of the TFT will do. But just like the way in standard Gromov-Witten theory, you're trying to integrate all of MGN bar, here we're going to try to integrate only over a chain in MGN, which excludes a little piece of MGN bar, and then add up recursively new components. So next time we're going to have to explain how to add this piece, which is missing from the integral over all of M11 bar. Any questions about this? Sorry, scrolled.
Andrei, can you scroll up a bit? I'm still trying to write down the degree of homology class at the very bottom. Nope, not the other direction.
Oh, the other direction, yes.
No,
6G minus 7 plus 2n. So the dimension of MGN, the real dimension, is 6G minus 6 plus 2n. So of course, for a non-compact, it's a manifold or a rational homology manifold. So H, the top dimensional homology would be 0 anyway because of Poincare duality or something of that sort. The non-trivial statement is that if you go one less from the top dimension, it's still 0. But this is a standard known fact.
So I mean, Andrei, the insight here is, so I mean, my sense is that what you're defining is a tubular neighborhood. You're removing a tubular neighborhood of the boundary.
Exactly, that is word for word.
The statement isn't so much that that's a chain, which it sort of obviously is, but that it has this nice recursive structure.
Exactly. The quantum master equation, which I've written somewhere here, this one, is telling you how to recursively, it says, if we defined VGN, first of all, in this geometric setting, it would satisfy this recursion. But then because of uniqueness, if we tried to give some kind of definition of what VGN is, if we didn't know what epsilon was and what hyperbolic metric is and so on, we could define VGN by saying, let's pick some solution of the quantum master equation, because anyway, any two solutions will be homotopic to each other. So for us, it will not make a difference under integration what they give. Yeah. So the approach we take is actually that this definition of Zwiebach and Sen, them being physicists, has these quotes here which kind of cause trouble. There are now some solutions to fixing this, but anyway, this is hard to compute, this VGNs. There is no combinatorial model in which we could compute these directly like this. But the idea is they satisfy this recursion, and any solution to this recursion will be equivalent to any other solution. So why not take some solution of this recursion as our solution of the quantum master equation that we care about? We think about it in the back of our minds as having this geometric interpretation because of this Zwieback-Sen picture, but for our purposes, we could take any solution VGN, and this we can resolve recursively. Just like I told you somehow, here we start with S03. If we could compute explicitly what delta of S03 is, not in this model that I was picturing here, but in some other model, and we could find some S11 which bounds S03, then we'd know what S11 is. Then we could write this, for example, another equation here would be that delta of S04 is 1/2 bracket S03 S03. We know what S03 is. If we could, in some model, calculate the bracket of S03 with S03, we'd find something, we'd try to solve for something, some chain whose boundary is that. And that would be our S04 because we know that that's unique. And the fact that this has a solution and it's unique comes exactly from this homology group being 0. Any other questions? All right. So now the moral, here is where we stand, and I will have to speed up a little bit next time to get through everything, was the moral is the following. If we could find this V explicitly and write down the TFT action rho A explicitly for 0 inputs, we could take beta, which would be rho A of V, as our desired solution of the quantum master equation in f of L. So again, we were trying to find a solution of the quantum master equation in the Fock space associated with L, the chains, Hochschild chains on A. So far, we can't quite do this yet because there are two problems. One is that V cannot be computed explicitly. I have given you a model using singular chains, but of course, we can't write down many singular chains very clearly. And also, everything happens in moduli spaces of Riemann surfaces with 0 inputs. I forgot where I wrote this. Here, you see I have 0 inputs. So I do not know how to apply the TFT action for 0 inputs. Those are both problems we still have not solved. But at least now we know if we could do this, we could find a solution of our quantum master equation, the distinguished solution that we want. Secondly, this would give us a homology class by taking exp beta over h bar for the operator b plus ub plus h bar delta. This is not good because we want a homology class for just B. right? Because we want to end in sim hat h bar of the Hochschild homology of A, bracket minus bracket, blah, blah, blah. Okay, so we want to get something that's closed under the operator just B. So the idea, the second idea is we will use the splitting, which we have not used at all yet, as to get rid of big B and delta in here. All right? Any questions about this? So this is where we are, but we still have some ways to go to do some explicit computations. So our goal is to be able to do explicit computations. So we need to be able to find V explicitly. We need to write down the TFT action for 0 inputs explicitly in some way, and get rid of B and delta explicitly using an explicit splitting. So I'm a bit over time, so I'm going to stop here. Next time, I will try to explain exactly how our two papers, so everything up to here, I apologize, everything up to here is basically all of it in Costello's original paper. There is nothing that I've talked about yet that is new. The new stuff will come in the last lecture, where our goal is to find a solution to this problem that we can't calculate V explicitly yet. We don't know yet how to write down explicitly the action rho A, and we don't know yet how to get rid of B and delta. In Costello's original paper, getting rid of this B and delta was a big mess. So that's the really most incomprehensible part of his paper. We're going to do something very different, very clean with explicit formulas.